Good evening. Good evening, everybody. God, that yesterday people were tired. Yes. So let's start. Do you have questions concerning what we did yesterday? I think you remember this is where we ended the show yesterday. Yes, with this graph. So what we did yesterday, the last thing we did, that was factorial ANOVA when we look at two factors. So I don't know if there's any explanation. Is there any explanation? Is there any, okay, Jane has not joined also.
Yeah, hello.
I'm listening, sir.
You tried to provide the logic for interaction. I didn't quite follow, I must confess.
Okay, the logic for the interaction yesterday.
Yeah,
okay, yes. Okay, okay. The formula for the interact. Okay, I understand. Yes, I know that's where the yes. So what we'll do, you know, if you remember at the beginning yesterday, you know, yesterday we talk about ANOVA. What we thought when we use the libido, the Viagra data, and we talk about the if it's significant, we'll go on to do either post-hoc or contrast, plan contrast. So yes. The example we use is the example of one-way ANOVA. You know, after we discussed yesterday, and I introduced factorial ANOVA. And under the factorial ANOVA, you remember that there are 4 examples I gave there, if you look at the slide. So, and the one we did yesterday is even the first one, the independent factorial design. So after yesterday, I've made up my mind that if you look at it, even not many people even run the factorial ANOVA. If you can get yourself know how to run that one-way ANOVA, if it's significant, then how do you do post-hoc and or either you choose post-hoc and plan contrast. But to me, post-hoc is more straightforward. If I show you the result of what I did yesterday, I did for somebody. Not only I've done it for many people, but we use post-hoc. Even that one that they presented in the conference in Abuja, not many people, they didn't even understand. Even just one-way ANOVA with post-hoc, there was no even plan contrast. Can you see? Not many people, when they just say, they didn't ask questions. They say, when I did post-hoc, they say, when did this start? They were just lost because they've not heard of it before. They don't know how to do it. They just, okay, because I accepted what they could not critique what she presented. So what I would do is that I just to go back to throw more explanation on that factorial, independent factorial, that first one. Every other one also is in the module, but we will not talk about it because it's becoming more complex, and most of that you may not even need to run it. But if you need to run it, just a matter of going to revise the module and look at some of those things. Also, when they give me something to run, if I have not done before, I just read about it just to look at how, if I have done that, how will I do this? Just find out. So what I will do now is to go over this independent factorial design, the one we did yesterday. Those other one, we have data for that one, but we will not do it because they are just it cause more problem. So when we finish that, we'll now go to the non-parametric counterpart. The Krukawali, yes, we are supposed to do non-parametric counterpart. If we are not going to do ANOVA, if it's not normally distributed, well, we either use, if it's one way, we use Krukawali. If it is two-way also, we use Friedman ANOVA. So can you see now, Friedman ANOVA. So what we're going to do now is to quickly look at this independent factorial design and go over it so that we can grasp it very well. Then we now do the parametric. Yes, what I yesterday, you remember, because I know that you don't have problem with one-way ANOVA because we have discussed it before yesterday. I also talked about it yesterday, the way we use the libido on the plan contrast, everything. So that is the one we use as the basis for our understanding of everything. The Planck contrast goes up. But for all of them also you do, even all these other ones you do, factorial you do. But once you get the basic understanding with that one way, it's okay. And we are not really going over that one. So let me just go over this factorial, independent factorial design, and we'll go to non-parametric counterpart. You know, as I said yesterday, I said the factorial ANOVA is a concept. Whenever we are having 2 or 3 factors. So it's different from, we know that ANOVA is for 3 or more groups. But here now, we are talking of factor. Like for example now, the issue of Viagra we talk about is only one factor of Viagra. We just have 3 group: control, low dose, high dose. It's only one factor, use of Viagra. That is why it is one way ANOVA. But if, let's say, after we do that, we now say, okay, in between, we use that Viagra, we also say, okay, between, we want to know the performance between male and between maybe white and black, or between some people and other people. So in that situation, you have introduced another factor. In that case, is 2-way. Like the example we gave yesterday. Now we talk about scoring of effective attractiveness. We now look at 2 factors: alcohol intake and sex, male or female. Alcohol intake is just like the Viagra. No alcohol, 2 pints, 4 pints. Not like the way we say placebo, low dose, high dose. It's the same thing. It's one factor. That alcohol is one factor. They will now introduce another, which is sex, male or female. So that's what make it 2 factors. 2 factors we are looking at. And whenever you have more than one factor, it can be 2, it can be 3, it can be 4, as many as you include. It is called factorial ANOVA. Simple. When it's more than one factor, it's called factorial ANOVA. Like this one, example we use is 2 factors. So it's still the same logic. The sum of square, if you remember, at the inception, day before yesterday, where the understanding of ANOVA is that place where we talk about variance between and within, and total variance. That is where the understanding. Once you get that one correct, you have solved the problem. It's not a difficult thing to understand. Once you understand the basis of that, it is done. So just as the way we have total sum of square, I even went to town day before yesterday. Is it day before yesterday? Yes, when we started. To first of all talk about variance, what variance is. How you calculate variance from mean, square. You remove mean from individual, that's deviation. You square the deviation. When you square the deviation, you add it together. That is sum of square, and that is sum of square you are seeing here. That's sum of, it's as simple as that. Sum of square. It is the average of that. When you calculate the mean of that sum of square from the mean, that is the variance. And you calculate it by dividing with degree by degree of freedom, not the sample size. That is sample size minus 1. Simple. Degree of freedom. So the variance, the average of the sum of square is the variance. So you see, we still look at the sum of square total and break it down into variance that can be explained by the experiment. That is sum of square model. That is variance between. When I say model, variance between. So I will go say, as you know, you said yesterday. I changed that one to between, and residual mean within, because that's how model and residual is what they use in regression. It's a matter of time. This ANOVA will become academic exercise, as far people just be talking about ANOVA. It's going to be regression because it's the same thing. And when we do regression, you go to see the reason, because you know much more. It is easier to do. And all these ones say this factor. You put them multiple regression. You put them at once. You just do create dummy. Irrespective of the type of variable, either quantitative or qualitative, you put them there. The qualitative own, you create dummy for it. Simple. That is one thing with regression. So it's a matter of time. ANOVA will become things of the past. Just academic tests, because nobody will use it. Even now, I don't think we will use it like the way you use regression also now. It's becoming like that. But the issue there is that the logic is the same. So now, in two ways, the variance explained by the experimental, or which is the between, is made up of not one manipulation but two. Can you see? So when we did the libido, the Viagra data, that between, the variance between, which is the model, what account for it is only the libido, the Viagra you gave. That only that one variable. But in these two ways now, we are talking of alcohol and sex. Gender, yes, gender. So that sum of square model, which is between, is two things that make up that sum of square model. You're going to see the gender, the two factors, and their interaction, making three. Can you see? Those two factors and how they interact. So if it is three-way ANOVA, it's going to be more complex. Though it became logic, because you're going to see that the different interaction. You have the effect of the three interaction, you have the effect of two. It's going to be more complex. And that is why at that level, you just go for regression because it's more straightforward to use. So now, but in the simplest form for factorial now, two factors. In these two factors, you can see gender, that's its own. That model is made out of gender, one, made of alcohol, two, the interaction between alcohol and gender, three. And that is what you are seeing here. Therefore, we break the model sum of square into variance explained by the first independent variable, then variance explained by the second independent variable, and variance explained by the interaction of these two. Look at the picture. Sum of square total. Can you see? You know that this is the way it is. Sum of square total. This sum of square. Can you see? Sum of square model.
Yes, sir. Yes, sir. Can you go back to that previous slide? I wanted to see the last sentence.
Okay.
In the slide before this one, sorry.
And that's it. I put it. Look at it.
Okay, you said, however, in two-way ANOVA, the variance explained by the experiment is made up of not one experimental manipulation, but two. Okay.
That is, there are two issues there, two factors. In this, our example that we did yesterday is male in sex and alcohol. So, forget about the word experimental. It may not be experimental, but most of the time, the experimental is that I use this type of thing. I have many groups like that. They may not be. But look at it. So, can I move forward now? Ahead. So, now the variability.
Yes, sir.
The total variance, sum of square total, is broken, and we know that one, between and within. The between is the model. And that is the one that is explained by your study, either by your experiment or by the study you are doing. The one you cannot explain by your study is unexplained area of variability. But that model now is not only one factor. There are two. If there are two factors here, you're going to be broken down into three. Variance explained by variable A, that's factor A. Variance explained by variable B, which is factor B. And the variance explained by the interaction of the two. Can you see? Now, we gave an example of what we did yesterday. We talk about the data set. This data set, you have 6 groups of people. These 6 groups of people are defined by 2 factors. One is the alcohol and one is the gender. So for the alcohol, you have pint, no alcohol, 2 pint, 4 pint. Those are 3 groups. Therefore, sex, male and female. So you will now see that you're going to see female that is not taking any alcohol, male that has not taken any alcohol, female that have taken 2 pints, male that have taken 2 pints, female that have taken 4 pints, male that have taken 4 pints. 6 group of people. And each of these, as these are 8 in number, each of this group, you can calculate, look at the score or the attractiveness, the mate they shows. The scoring, you will see that there are mean, you calculate the means and the variance there. So you can have mean and the variance for each group. Now, you can have the total mean, the grand mean. The grand mean now, can you see, if you had all the 48, okay, if you have all the 48 together and divide by 48, that will give you the grand mean. Or if you had all the 6 mean together and divide by 6, it will give you the same. So the result we are seeing on that is when we do normally now, the first 2 column, this first column here, after the X, is deviation, is total. That one is looking at the total variance. You remove the grand mean from each value and square it in this second column. The total he gave is the total. I don't know why that thing is not started again. I want it to show. Yes, I've shrunken it. That's it. It gives you the total variance. Can you see? The first 2 columns, you know, calculate the total sum of square. The next 2, this one is the model now. Sum of square between. That one, you remove the grand mean from each of the. You remove.
Sir, you're breaking, sir. You're breaking, sir.
No, it's not me. It's Dr. Prof. His end is disturbing it. Prof, I'm trying to mute him.
I'm muted though.
Okay. But
there's no noise from my end.
No, it's propping. It's probably, I know now. I get it. There's not something, I don't know. Maybe is it that your phone is ringing? I don't know. Something is coming from your end. That's what is making it.
I'm trying to use my phone.
Maybe because if you are using your phone and the phone is trying to ring or whatever, it disturb the transmission. Because you are appearing in 2 places now. And is this other one that the second one that is the one that is not showing you, that's the one that is disturbing. The one that is not showing you is showing one light. The one that is not showing your picture, that's the one that is disturbing. Maybe I should remove it. I'll remove it now. Where do we remove it? Okay, I've removed that one. Okay. I think you can hear me now, right? Now.
Yes, sir.
Yes. So the second, the one in the middle now is the model. If you look at it, how you even know that one is, you know that you are removing grand mean from group mean, and there are 6 groups. You will see that the value you are getting will be the same for all the 6 in each group. Look at it now. Look at this one. All this value you are getting is for the first 6, it will be the same. For the next 6, it will be the same. For the next, like that. You know that because the group mean is the same from all the members of a group. So when you remove the grand mean from it, it gives you a constant value. I don't know if you get it now. So that's how you even recognize that is the one that is talking about the model. And if you look at the total, the sum of square for the model is 5,479.1672. And you know the total variance, sum of square is 8,966.6672. So the last 2 columns now, we talk about the variance, sum of square within. Because for each of the mean in each group, you remove that mean from each value in each group. You remove the mean for a particular group, from all the value in each group. And that you square it. That's how you get sum of square within, which is 3,487.5. Now,
please, sir, for that last one, I didn't get your explanation. That is, you remove the mean.
Yes, now this sum of square within. The mean for each, each group, there are 6 groups here now. 6, 8, 8,
Yes.
8, 8, and 6. Each of the 6 groups,
Yeah.
they have their own mean. So you remove the mean from each of the value in the group.
Oh, yes. Okay,
that's how I square it. That's how we get the sum of square within, and which is 3,487. Now, okay, that's what we summarized previously here. Can you see? The total sum of squares is 8,966.6672, which from that table. Then sum of square between model, which is between, there is 5,479.162. And the sum of square within is 3,487.5. Now, you know, if let's say it's one way ANOVA now, all you need to do is to calculate the F for each of them, and calculate the variance for each of them, for the between and within, and just divide between by the within. But it's not one way ANOVA. So you just first of all do that one now. Since there are 2 factors involved, you must be able to do also for the factor itself. You know, if you remember the previous one, each male and female, we split into either you are taking 1 pint and no alcohol, 2 pints or 4 pints. Or in another way of saying it, for each no pint, you split to male and female. For 2 pints, male and female. For 4 pints, male and female. Jane, you just join now. Okay. So, but here now, you collapse. That is, you consider the effect of the gender separately. In that case, all you need to do is to divide all of them into male and female. Forget about whether somebody is taking alcohol or taking 1 pint or 2 pints. You just say male, female. No, that is for gender. For alcohol also, you collapse them into no alcohol, 2 pints, 4 pints. Forget either anybody is male or female. Can you see that? So that is how to know the main effect of each of them. And that is what we did in the next slide. Can you see? We did the same. Can you see that? The first on the right is gender. This one is for sex and for alcohol. So what you are doing, if you look at it there, you are not looking at within or total. What you are looking at is the sum of square between. Can you see that? If you look at it now, what you do now, you know the way you have done for, you split the gender into male and female. They have their own mean also. Mean for the female, mean for the male. The way you split for alcohol, no pint, 3 pints, they have their mean, 3 means there also. For no pint, 2 pints, and 4 pints. So it's the same thing. It's the mean now. You now remove grand mean from each of the mean and square also. Do for male and female. Yes, I'm now. You remove the, no, you have, they are 48. You're going to have 24 male, 24 female, 24 female, 24 male. So you remove the grand mean from the mean for this, the first 24 now. You remove grand mean from the mean of that mean. If you look at it, you're going to get the same value for them. Can you see? Then the next one, you remove grand mean from the mean of the male. You get the same value for, when you square it and sum it, it gives you the, this is now, let me do the same thing.
Sorry, sir, you said you remove the grand mean from the
Yes.
mean of the male.
Yes, I'm on this. Yes. Look at it now.
So
Look at it now. It's the same logic. Look at, when you put this table for the effect of gender, you only divide the whole people into male and female. Forgetting about whether anybody take alcohol or you divide to male and female. Each of them, look at it, you calculate their mean, and the mean for male, the mean for the 24 male, the mean for 24 female. The same thing when you divide them into the 3 alcohol group, if irrespective of their sex, you have the mean, you calculate the mean for, it's going to be 16, 16, 16 now. The mean for the 16 people that took nothing, the mean for the 60 people that took 2 pints, and the mean for 60 people that took 4 pints. So it's the mean you now use to do the sum of square within what they contributed. You just remove the grand mean from the group mean and square it. If you look at it for the gender home, you arrange it 1 to 24 is female. Then 25 to 48 is male. For this one, because they are divided, the 1 to 16 is no pint, no alcohol. Then 16 to 32 is 2 pints, and 33 to 48 is 4 pints. And if you are looking at it, how you know, you look at it, it will be the same thing for those who are in the same group. And you see the same value for those that are in the same group. But you look at it. When you see, so this one is to look at the effects, the contribution of both gender and alcohol. If you look at it, the total sum of square, for gender, contributed for that model, contributed by gender is 168.7512, and the total sum contributed by alcohol is 3,332.2922. And if you add the two together, look at it, the same thing we put here, 168.7512, 3,332.292. If you add the two together, it's not up to the total, it's not up to the sum of square between we have calculated before. Because that sum of square between we calculate is 5,479. So the difference is the interaction effect between them. Yes or no? So the main effect of gender is this, and the main effect of alcohol. The interaction effect would be you remove the 2 from the sum of square model, that is sum of square between. When you remove it, it gives you 1,978.125, which is the interaction, that is the effect. What is the effect contributed by the interaction, both of them? It's just like you and your friend, you have some things together. You keep your property. So you own your own property. Your friend owns your property. There's some property you own together. And maybe even husband and wife may do that also. There's something that husband has, something wife has. There's something that both of them have together. So that is the interaction. The interaction. So I don't know if there's any question concerning that before I move forward. Any question? Because you need to get it right. There's no academic something, it's just you must be practical. Any question? So I should proceed, right? Okay. Now, after you have done that, okay. After you have done that, now you now come. No, it's the sum of square you have just calculated. You now want to calculate the variance now, which is mean square variance, so that you can calculate the F ratios. So here now, we know that the variance for A, which is gender is the A factor here. The variance, which is sum of square, mean square for gender, will be sum of square for gender over the degree of freedom of gender. So you know that how many value does the gender have there? How many possible values? How many groups? 2. So the degree of freedom will be 2 minus 1, which is 1. So that's why you divide the sum of square over 1. So this is the variance now for gender. Now, the variance for B, which is the mean square for the second one, which is the alcohol. I will have put alcohol there. Maybe I should have put alcohol. Then I'll put it in the slide like that. So it's going to be sum of square over degree of freedom. And how many groups does alcohol produce here? How many groups?
3.
3. That is no.
You have none, 2, and 4 pints.
4 pints. Thank you. So the degree of freedom will be 3 minus 1, which is 2.
Okay.
So when you divide the sum of square with it, it gives you, this is the variance. The variance for the interaction between both of them, gender and alcohol, is the sum of square over the degree of freedom. The degree of freedom, how is it 2? We have 2 groups of gender and 3 groups of alcohol. You know the degree when you cross tabulate. 2 minus 1 times 1 minus 1. So yes, row and column minus 1, yes. 3, the alcohol is 3 groups, 3 minus 1 making 2. The gender is 1 group, 2 groups, 2 minus 1 making 1. 1 times 2. Making 2. So the degree of freedom is 2 for the interaction. So it gives you this. So now, you know the residual has its own something also, because we are in the initial you have calculated the sum of square for which is the within. The residual is the within, sum of square within. And so the variance within will be the sum of square within over 42. You know, the total is 48 and 6 group. You can say 48 minus 6, or you say 8 minus 1 times 6, because each of them 8, 8, 8, 6 group, 8, 8, 8. Each of them is 7, 8 minus 1, which is 7. 7 times 6, 42. Or you say 48 minus 8. Give you minus 6, 6 group. 48 minus 6 give you 42. Whichever way. So you add it. Yes?
48 minus 6.
Okay, don't say that. There are 6 groups. There are 6 groups. Each of them is 8, 8. So the degree of freedom for each of them is 8, 8 minus 1, which is 7.
Wait. No, I didn't get. You said there are 6 groups.
So, let's go there. Look at it now.
Okay.
Male, female, true.
Male, none. Female, 2 points. Male, 2 points. Female, 4 points. Male, 4 points. I didn't know 6.
Oh, okay.
So each of them is 8, 8. Each of them is 8, 8 in number. So the degree of freedom for each of them is 8 minus 1, making 7. 7 times 6, 42.
42.
So the degree of freedom for within is 42.
I'm not understanding. I wish that. So isn't there like a formula for it? Because I don't understand how you calculated this last one. No. Because the degree of freedom I've always known is either n minus 1 or rho minus 1 times column minus 1. So I don't know how you got this other one now. So are you laughing at me? Please help me. How to understand?
Let me explain. The degree of freedom is entity minus 1. Entity. The entity can be, and that's where the entity can be anything. It's only that when you conceptualize it for categorical and quantitative difference. For categorical, you know, if you say ethnic, sex now, we have 2 possible values of sex. The degree of freedom will be 2 minus 1 for sex. Yes, I mean.
Yes.
If we talk about our geopolitical zone in Nigeria, there are 6.
Yes.
The degree of freedom will be 6 minus 1.
Minus 1. Yes.
If we talk about ethnicity, when you are breaking your ethnicity to maybe 4, the way you usually say Hausa, Igbo, Yoruba, and others, 4.
Yes, sir.
The degree of freedom will be 4 minus 1. For categorical variables, the degree of freedom is number of the category minus 1.
Yes.
But when you now look at an association between 2 of those categorical variables, the degree of freedom will be the degree of freedom for this one times the degree of freedom for this one. That was what we did in
I didn't know that.
Yes, now that is where you get the rho, all these rho minus what and so on. You know, when you are looking at association between categorical variables, you are doing chi-square, you cross tabulate. When you cross tabulate, one will be along the row, one will be along the column. So the degree of freedom, actually the degree of freedom for the 2 is a product of the degree of freedom of the 2. If the row is 3, the degree of freedom is going to be 3 minus 1, which is 2. If the column is 2, we have to go to 2 minus 1, which is 1. 1 times 2 will be 2. The degree of freedom for the 2 of them combined will be 2. Do you get the vision now? That is for categorical. Then when it comes to quantitative variable, because the quantitative variable, they don't come in category, because you can have infinite number of value. You understand now? So you don't categorize. What if the number, the sample size -1 is the degree of freedom, because any of the entity can change. You understand now? If your sample size is 400, the degree of freedom is 400 -1. You get the picture now?
Yes.
So when you are comparing,
I understand.
When you are now comparing two groups, the degree of freedom for the two groups will be, for each of them, you add it together. Like you add it together, you are not multiplying, you add it together. Like if there are two groups now, each of them 20-20, the degree of freedom for each of them will be 19, then 19. Total will be 38, 19. Or you say, add the two together and minus the number of group, -2. And that was what we did. That's why they will tell you that the degree of freedom when you are doing t-test is n1 plus n2 -2. Because there are two groups. Yes, I'm not. It's like say n1 -1, n2 -1. The first group -1, the first group -1. That's all. You add it together. Or you say you add the two groups, you minus the two. You get the picture. So it gives you the same thing. Yes, so that's what we have done here. There are 6 groups here. So the degree of freedom for each of them is 8. Each of them is 8.
8 minus
8 minus 1. 8 minus 1, 6 places. Make it 7 times 6. 7 6 places give you 42. Or you add them together, which is 48, minus the number of group, which is 6. It gives you the same answer. So is it clear now?
Okay, so for this one now, 8 minus 1 in 7 places. So I want to go, let's go to that formula now.
6 places. In 6 places.
Sorry, 6 places, I mean. I understand this one. So I want to see how you did. The next slide. I want to see how you now go, because I saw 42.
7 times 6, what is the degree of freedom for each of them now? What is the degree of freedom for each of them? There are 8 people. 8 minus 1 is what?
8 minus
1 is what?
1.
8 minus 1 is what?
7.
Sorry, sir. I will call you back, sir. I'm in a lecture. I will call you back. I'm in a lecture, sir. I'll call you back. 7.
8 minus 1. 8 minus 1 is 7. 7 times 6 is 42.
So where are you? What is the cause of the matter now? That's it. That's why the degree of freedom is 42 there.
Okay. I now understand.
So that's why the degree of freedom is 42. So
I know.
When you divide that one by 42, it gives you the 83 point. This is mean variance within. Now, for you to calculate
it's within.
It's within. So I remember it's the within that usually have everything together and usually give you the biggest degree of freedom. Yes. Now, the F ratio of the two independent variables and their interaction can then be calculated by dividing their mean square by the residual mean square. You divide each of them by the within. Yes, can you see that? All of them you have calculated. Look at them off. 1, 2, 3. You divide each of them by within. That's your F. When you divide each of them by within, this is what it gives you. Can you see? 2.032. That is the main effect of gender is 2.032. Yes. The main effect of alcohol is 20.065. It shows you that alcohol contributes more. Yes. So the interaction effect of both of them is 11.911. So as you're going to see now, when we analyze, you discover that the gender on its own is not significant. The alcohol is significant. The interaction effect is significant. Any question? That's when we now went to run it yesterday. So should we rerun it now? Somebody should rerun it for us so that we just look at it and go. So that it can stick, so that we can just start our non-parametric counterparts. Who will rerun for us? Let me stop sharing. I want somebody to rerun. I don't want to call names. Somebody should volunteer and share.
We need to rerun it.
It's the beer Google's effect. That's the data. So who is doing it for us?
Lisa, while we are doing that, I just wanted to go back. You know, when you were teaching us on just that normal ANOVA, where we're doing the sum of squares for between over sum of squares for within. You know, whenever we do the degree of freedom for within, it was always that total number, or that is the sample size minus 1.
No, it's not true. No, that one is the total sum of square. If you want to do for total sum, all of them combined.
Yes.
That would be total minus 1, but it's not for within. It's going to be the total minus total minus the number of group.
Okay.
Or each of them minus 1 times the number of group, whichever way, it will give you the number of group. If you remember for that one, the degree of freedom was 12 for the libido, is 555, make it 15. So you can say the degree of freedom was 12 for within, which is 15 minus 3 because there are 3 groups. Or you say each group 5 minus 1 in 3 places. 5 minus 1, 5 minus 1, 4 times 4, 4, 4. 4 plus 4 plus 4, it gives you 12. So whichever way you do it, give you the same.
Yes.
It's the total sum. If you want to know the variance total, that give you say the degree of freedom is total minus 1. And if you look at this one now, we say the degree of freedom for this factorial.
Okay.
The degree of freedom is 2, 1, 2, 2, and 42. And the overall degree of freedom will be 47. If you add all those two together, it will be the same. You get the picture now. If you add all the degree of freedom, it will be up to 47 because for gender is 1, for aqua is 2, make it 3. For interaction effect is 2, make it 5. Then for the within is 42, make it 47, which is equal to total degree of freedom also. So
8 minus 1.
Yes.
Okay.
So who is sharing? Who is sharing? Nobody. I will call him. Jane, you can share now.
Do we need to rerun it?
Okay, we don't need to rerun it, right? Okay.
We don't need to rerun it.
Okay, there's no need. Should we go ahead and just go to the next thing? People should talk. Oh, I don't know.
Oh no.
We should not rerun it, have we? Let me just show you the result because the result is already here also.
Okay.
The result, when you run it, if you look at it, you'll be looking for Can you see gender? Can you see something? Let me. Can you see this table? Test between subject. Can you see? If you combine everything without looking at the effect, this is what you get. But if you look at it, intersect, look at the gender. Look at the gender effect. Can you see? Can you see? Is it not the same thing? The F, is it not 2.032 we get? This is the p-value. Yeah. For aqua, if you remember, it's 20.065. Can you see? It's significant. For gender times aqua, that's their interaction. Look at it, 11.911 p-value. Can you see?
Yes, sir.
Very straightforward. This one is just the 11 test for homogeneity of variance. See that it shows that not significant. Their variance are not different. So you can use parametric test. That's what it's telling you. It's just proving that you can use parametric test. Then this contrast. We did contrast yesterday. It may, now that it's significant, if you want to really know where the significant lie, that's where the contrast comes in. Let me see if we have, okay, these are the interaction effects. This graph, the first one show only alcohol. You know, that's alcohol that is significant. Now, if you look at it now, you will see that where the difference, even from the graph, you can know where the significant lies.
Yeah,
right?
the 4 points.
Yes, you know that it's between, because there's no difference between no point and 2 points.
Yeah.
Is the where the difference lies is between either no point and 4 points,
And 4 points or 2 points.
It's mainly 4 points destructive.
And the 4 point is the one that has reduced attractiveness, the effect of 4 points. So if you look at the gender, the attractiveness is lower with male, but you can see that the reason is not significant because it's very close. The values are very close. That's why it's not significant between male and female. So these other 2 graphs show interaction, just how they interact. You can see from all, it shows that for all of them, you can see it's very funny. Can you see this one now? The 4 points, it affects male more than the female, but the attractiveness is lower among female when they didn't take any drug, right? Or when they just take small drug, but the attractiveness is lower among male when the pint is much. So it shows that the pint has effect more on male than female. And this graph you are seeing the same thing. This is the line graph. No, it's just, this is just the line graph.
The males are more
affected.
The alcohol effect on them is more.
It's more, yes. So when they take more, they misbehave more than female. That's way.
The female living with the alcohol, they are still wise.
Yes. Okay. Okay. I think we are done with that. Let me just quickly share the. So okay, before I do that, so that other thing I will still share with you in your module. Other aspect, the factorial repeated measure. You know, maybe we should just go around to well, it is more necessary. We are not going to run it. This is other thing under the those factorial. They are more a little bit more complex than the one we have just done. That one you get it in the module and just read. Let's just go to
the concept.
Oh, okay. I just share the concept. Okay. Okay. Because it's going to raise more questions than you expect. Now, factorial repeated measure is employed when there are several independent variables by the same participant. What it means, you know what we mean by repeated. It's just like the pair, but this one is not just pair. Maybe what we call it repeated when it's 3 times.
Once.
You take measurement on the same set of people 3 or 4 or more times. That's repeated measure. So the same set of people. In order for it to be applied to a set of data, assumption of the consulting sphericity must be met in addition to other assumptions that are required in one way and another. You know, the one way and another, the assumption we require is the assumption, normal assumption for using a parametric test.
Parametrics.
Yeah, but this one go beyond it for the repeated measure. You go with the consulting sphericity of circularity. It means equality of variances of the difference between the experimental level. You know, when we talk about homogeneity of variance, the different group, equality of variance. But this one, that's sphericity. You know, when you do repeated measure in between, that is the same set of people, you took measurement 3 times. The difference in their measurement is what we are talking of now. It's not individual measurement now. Can you see now? In the difference, if the mean for before at the initial is this, and you now have another mean, it's the difference between the mean. So the variance of the difference between the first and the second, and between the second and the third, the difference in those 2 stages, the variance must must be the same. That's what we call sphericity or circularity. Now, if you are to take each pair of experimental level and calculate the difference between each pair of the score, then it is necessary that the difference have approximately equal variance. That's what we just said now. Therefore, one need at least 3 conditions for sphericity. So you cannot, if you are not taking measurement 3 times, you cannot be talking, of course now, I don't even talk about ANOVA. It's going to be pair t-test. So you cannot talk about sphericity if you have not taken measurement 3 times. Note that the sphericity is a more general condition of compound symmetry. That compound symmetry is just a hold that both variances across conditions are equal and covariances between pairs of conditions are equal. It has been shown to be a sufficient condition for ANOVA using repeated measure, but it is not necessary. The compound symmetry is bigger as per it. The variance must be equal, the covariance must be equal. If that is met, well, it's good. You can do your repeated measure, but you don't actually need it. So it's just part of it is the sphericity, which is the circularity. This one just demonstrated this thing, what we have just said. This was just for demonstration. Look at it. If you take measurement A, B, C, A minus B, when you look at the difference between group A and group B, then there is a difference between A and C. There is a difference between B and C. The differences you are seeing, the variances must not differ. You understand? That's what they are saying. The variances must not differ. No. When some pairs of variance are equal, while some are not equal, the data are said to have local circularity. So assessment of sphericity is done by using the do consulting much-leak test. So when you run the data, it comes out. So in this case, there are 2 different F ratio you get for this. F, they just give this sign.
Prime.
Prime. What do you call it, sir? Prime.
Prime.
Prime. F prime and double prime. So the F prime is what is usually used. This is the F ratio derived from the mean square of the comparison in question and the specific error terms of the comparison of interest. This is the F ratio normally used. The other one is derived from total error mean square for all repeated measures. So for this one to be valid, that second one, overall sphericity must hold. The whole data set must be spherical. But for F1, this first one to be valid, sphericity must for specific comparison in question. So this first one is the statistic generally used, and the effect of violating sphericity is a loss of power. An F ratio that simply can be compared to total tabulated value of S distribution. So if the sphericity, just like the way the condition for doing parametric cell is not met, in this case, what will happen is a loss of power. Loss of power means that you may not find a difference. Actually, when difference is there, you may not find it because there's loss of power. And that's what we usually do also. That's all the logic behind using non-parametric. So options, if assumptions of sphericity is violated, the things you can do, they are very funny. You can go to Greenhouse-Gresser correction or unfair correlation. This one just academics on multivariate analysis of variance. Theory of one way. There's something I just wanted to pick here. If this is what you just picture, you just pick. It makes sense. If you look at it, look at this picture. In repeated measure ANOVA, the model and residual sum of square are both part of the within participant variance. Can you see? If you remember, for independent, the model and residual. Can you see now? The model and residual sum of square are both part of the within participant variance. Can you see? If you remember the independent, the model is between, right? It's not within. But in this one, because it's the same people you take measurement from. So the model and the residual, they are within participant. It's not between participants. Can you see? Both the model and error, they are within participant. That's a very so I think we should just stop there, because by just illustrating, okay, I can give you just illustration, we will not run it. The illustration here is, they say a celebrity was forced to eat 4 different animals. 6 insects. No, what really happens that they are strange food they give to 8 people. They give it to all of them. When you eat stick insect, they try to calculate for how long did you retch. You know the more retch, as if you want to vomit. Thing like this. So for how long? They calculate the time for how long each of them retch when they give them the insect to eat. After that, they give them kangaroo testes to eat. They calculate the time it took for them to retch. They give them fish eyes to eat, and calculate the same set of people. Or then we eat crop to eat. Which crop is larva? No, the larva of butterfly, some people eat it. So this is larva. This which crop is larva, like larva. Now, the mean time for this mean time you are seeing, can you see now? Alone now, this one show the mean time. This number 1 person, maybe this one Joseph. This is the time Joseph for each of the animal. The mean time for is the mean for all this. When you add all this, divide by 4, and this is the variance. But along the vertical for the stick insect, the mean score for all of them is 8.13. For the kangaroo, can you see now? Along the horizontal and vertical, you calculate the mean. So you will see something. This one you are seeing, the mean here is within, because if you look at it, 8711 is this same number 1 person that scored all this. So this mean and the variance is variance within participant. And what you are seeing here is the variance between participants. You can see now, when you come down here, when you see the mean is between. This is the grand mean when you and the grand variance. So this one just give you
sorry, sir.
Yes.
You said which one is the variance between? You were pointing at something.
Between is, if you look at it now.
Yes.
This is number 1 to 8. These are different people. You can give them names.
Each person. Yes.
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 So all of them is all the food.
Yes.
Now, these are the time they spend to retch for each of the food. So if you say for stick, and you calculate the mean here, you are adding the time for all of them together and calculate the mean.
Yes.
So if you calculate variance for it, it will be variance between them. Because you understand me, I don't know if you understand me. You know, if you calculate, I don't know if you understand what I'm saying.
Oh, I understand what you mean. Yes.
They are different people.
I understand. Because each person, they are different people. Yes, I understand. Yes. That's on the vertical axis.
Exactly. For each of these, the vertical is there because it is between you.
Yes.
What you are getting here is between.
But horizontally,
if you do it horizontally, it's the same person that eats the value for the same person. What you get here is within person. Within participant, the air is between participants. You know, those are the logic once you get it right. Okay. And they now did this sum of square also here. Sum of square of the first one did the one. If you look at this one, you will know that
the bush.
Yes. If you see this value here, the way they do it, you know that this one, they first of all do the within participant. This is within participant here. Calculate the within the participant. Here, this one calculate the between participant. Can you see? So the total sum of square is this. The sum of square model is this. Between participant sum of square is this. Within participant sum of square is this.
Okay.
The residual sum of square will be within minus model. It give you this. Calculate. Don't worry. Don't ask me a question. Let's just stop it there. Because I know they're going to waste our time. No, I've already said it, Dr. This thing. Actually, in our training, we have even give too much to a lot of advanced things. You understand me now? So, and it will confuse people. Yeah. What you can do is that we have the module. If anybody want to read it, you read it. You can, if you have questions, you want to analyze such thing, you can ask me. Because even doing only one way ANOVA and know how to do post hoc is enough. Yes, I mean, it's enough because not many people can do it.
Parametric now.
What do you say, sir?
Non-parametric.
Yes, that's what I want to go to.
Move on.
Yes. So
move on.
Yes. Non-parametric counterparts. So what's the time now? Do we need to?
Sorry, sir, will the video not be full lengthy?
Yeah, so that the video will be
clear. So that, yes, because yesterday I was able to send 3 of those videos to you, which is okay. And you can, okay, let me stop and log in again.
Yeah, yes.
I will try to, I will just log in immediately. I will try to come immediately.